Hi, everyone. Hello and welcome to the 13th day of Architizers Future Fest. We are midway through the final week, which is focusing on the future of architectural materials. So for everyone who's attended any of the previous talks this week, welcome back. And if this is your first event, thank you for joining us. Future Fest, for those of you who don't know, is a 3-week long event featuring a range of A+ award-winning architects from around the world, forming a vibrant celebration of architectural innovation. It's also our way of warming up for the 11th annual A+ Awards, which launched this October. I'm going to give you some more information on that a little later on. For those of you who don't know me, I'm Hannah Feniak, and I'm the architecture editor at Architizer. Today, I'm delighted to have the opportunity to chat with Leslie Locke, co-founder and principal at HANA and assistant professor at Cornell University's Department of Architecture. Through Hannah's recent work on robotic timber fabrication and concrete 3D printing, Leslie will share how digital fabrication technologies facilitate new material methods, tectonic articulations, environmental practices, technological affordances, and architecturally expressive forms of construction. If you'd like to learn more about Future Fest and to see our full schedule of talks, you can go to architizer.com and click on the very top article. Here we list the names, times, and dates of each talk, along with a short description of what type of content you can expect each speaker to cover. From this article, you can also register to and access past events in order to kind of see the recordings of talks that you've missed. While we continue to wait for the room to fill up and for people to log on, I want to encourage you to all say hi in the chat box on the right-hand side of your screen and to let us know where you're from. Today, I'm tuning in from Valencia in Spain. So while we do that, I'll share a few tips and quick pointers about our live platform. And I've got a handy slide here. So firstly, if you're having any technical difficulties with the stream, you can click the help icon in the bottom left-hand corner of your screen, and you'll see a few options for improving your picture, the sound, and so on. More often than not, issues with the sound and picture quality can be resolved simply by refreshing your browser. So maybe try that first and you'll catch back up to wherever we are in the talk. Anything you do miss, as I mentioned, you can access through the recordings later on. Secondly, it's worth noting that there will also be the recorded version of the talk. And so you'll receive that in your email afterwards to catch up on anything you miss. And you can also feel free to email that forward that email to your colleagues and friends after the event so that they can register and watch the talk. Thirdly, we encourage you to use the chat box to discuss and comment on Leslie's presentation. But if you do have any questions that you'd like to ask Leslie at any time during the talk, you can simply click the questions tab that's in the lower bottom right corner of your screen, just next to the chat icon. If you can then also upvote other attendees' questions, and we'll aim to ask the most popular questions. Finally, I want to draw your attention to the React button, which is in the central bar at the bottom of your screen. So right in the middle there. You can there select a small handful of emojis, and whenever you see something that you like, you can use them to kind of demonstrate that you're engaging with the talk. Thanks to everyone who's hitting that now. And now, finally, allow me to introduce our guest for today. Leslie Locke is a co-founder at HANA and an assistant professor at Cornell University's Department of Architecture. Her experimental design practice, HANA, utilizes innovative forms of construction to advance building practices. The work aims to mine the tension between machine means and architectural ends. At Cornell, Leslie directs the Rural Urban Building Innovation Lab. Working with non-standardized materials and biomaterial, her research and teaching explore the intersection of technology, novel material methods, and urbanization. By studying regional behaviors from spatial transformations to material resources, her work contextualizes design strategies with computational protocols and technologies to customize unique needs for local communities. Thank you so much, Leslie, for joining us today. Without further ado, I'm going to pass the mic off to you.
Thank you, Hannah. I will share my screen. And thank you everyone for tuning in today and joining the talk. I'm connecting through from Ithaca, New York. So fall is here. And so the title of my talk today is Unlogging Material Narratives. And first, I would like to thank you, Hannah, for the kind introduction, and also to Paul for the invitation to share our work from Hannah with the Architizer community. And so the projects I'll be sharing today is developed together with my co-founder, Sasha Zhivkovic. So, by the way, the video might be a bit pixelated, but it's okay. So at Hannah, we believe that the issues of making and forming are fundamental to how we operate as designers. And the various projects presented today will seek to inform form through a variety of methods of production. They range from digital fabrication technologies that facilitate new material methods to also a combination of conventional methods as well, to think about tectonic articulation, environmental practices, technological affordances, and different forms of construction. And so in the past few years, we've created open source construction machines, which we argue inevitably affect how we think and design through making. And in our work, we, as mentioned in the introduction, we really seek to mind the tension between the machine means and the architectural ends across scales. And so to think about how our tools and our processes can influence the way we can build, but also ought to build in the future. And by developing our tools in the past several years, we built an infrastructure and framework for architectural explorations, starting from the design of the tools itself to prototypes, installation, and to small buildings, and next step, current step, into a larger building. And just like this video here, like the robot and the animation, we have been trying to unlog our own architectural preconceptions and expectations. So there are certain concerns that drive our work that are architectural, spatial, material, environmental, and technological. And for our talk today, I would like to use the concept of unlogging to unpack some of these concerns and their conceptual entanglements in the presentation today. A log is both a part of a tree and also an official record of events through a voyage of a ship or aircraft. New material and design practices are needed to address climate change as one of the most pressing problems of our generation. So moving forward, designers and researchers need to develop new logbooks, log new design protocols, and fundamentally unlog our past loggings in order to move towards more radically sustainable and less wasteful building processes. And one of the main environmental narratives that we've been engaging in the past several years is actually with this tiny little bug called the Emerald-Ash-Borer. It is a small beetle whose larvae hatch underneath the tree's bark and cut off vital layers that transport nutrients within its trunk. And this EAB, in a way, it's an invasive species that threatens the ash trees in North America. And so currently, there are 8.7 billion ash trees in North America that has been drastically transformed by the EAB's existence. And as of October 2018, it is found in 35 states and several Canadian provinces. And as a reference, we're based in upstate New York, almost every 10th tree in New York State is ash tree. So every 10th tree we see will be eliminated, felled, or destroyed by this EAB epidemic. And so while we as designers cannot help the dying trees, we do believe that the infested wood forms an enormous and untapped material resource for sustainable wood construction. This problem really came to our attention when the EAB arrived at Cornell at our doorstep in 2018. And it has since become our own source of what we call morbidly sustainable material. And this is one of the infested logs that we used in one of the projects I'm showing today. And you can see the markings created by the beetle larvae between the wood and the bark. And so the first project is called Unlog. It's curated by Katie McDonald and Carl Schumann from UVA, and it was commissioned as part of the Bio-Building Material Exposition. In this project, Unlog questions current paradigms of timber framing by working with local forest resources and trees that are devastated by the ongoing Emerald-Ash-Borer epidemic. Conceptually, this project investigates how far a single log can be stretched, both literally as an assembly and also figuratively as a valuable resource. The research focuses on the development of a lightweight and easily deployable timber framing method, utilizing robotic curving techniques to transform the EAB-infested trees into material efficient and valuable resource. So here you see the installation pavilion on site. One of our audience here, Rafi, is from UVA, so he saw it in person. And the departure point of thinking about contextualizing, the framing as a technique is that in the US or in North America, wood framing is a quintessential expression of the construction and culture. Today, over 90% of new residential buildings in the United States are made from fast-growing softwood timber that is first milled into dimensional lumber, such as 2x4s, and then assembled into wood frame buildings. So for us, we ask, can we make this method of construction more efficiently or more materially efficient? Can we use these decaying hardwood to rethink framing techniques? And so here, the logs used in the Unlog, essentially the logic is that unfold from a line to surface, loosely referencing and reinterpreting the tradition of wood framing. In this drawing, which shows the log utilization comparison of, let's say, conventional framing, where you see the 3 logs and the 2 buys that are extracted from it to produce a frame wall, versus the strategy of actually curving a log, splitting in half, curving, and then stretching it to create a panel. And so it's also important to note, our practice research also is linked to our teaching sometimes, and the full log curving method was developed by one of our previous students, Savannah Chazen-Hogg, in the Timber Villa Option Studio at Cornell in 2017. So as a comprehensive method, so from there we develop a comprehensive method for this full log curving. And so in general, more broadly speaking, curving is a relief cut technique that induces flexibility into material and is often applied to sheet material to generate curvature. What we're doing here is we are using curving in a different capacity by curving along the length of the log. And so this diagram shows how when you cut in an alternating pattern, we are able to unravel the volumetric round wood into an operable leaf spring component. And so here's the diagram illustrating the geometric relations between the uncut margin depth and the component transformation. So by determining how much we curve, we can begin to calibrate the density and the flexibility, stretchability of the component. The zigzagging logs can also be used to create brace structures, and according to the sort of natural geometry of the log, by using the robotic curving, we can also reflect that curvature in the curving pattern as well. So that way we can not only just curve straight logs, but also curve logs. The structure is partially inhabitable, and we review the unique wood grain and profile of each log. So here's the axon that shows the structure sitting within the site. We actually have a quite amazing site with 3 huge trees. And so when we first approached the design problem, we were thinking, well, how do we start to orient the structure within the context? And so the idea is that the 3 individual A-frame can be oriented each towards one tree to frame a view. So here is a script that we developed to explore the various spatial configuration. And here shows the final configuration on site, where you see this sinuous structure nestle between the trees. So essentially it's 3 A-frame that is connected by 2 curved panels. And here's a view of showing how one of the A-frame is directing towards the context. And this image here shows how it arrives on site. Basically, we have 6 logs that weigh less than 2,000 pounds, and then it's about 250 pounds per log. And you see the threaded rods, the hardware, and the ground anchor that we bring on site. And here, in general, this drawing shows the workflow of the project. So we start with the log, with the tree logs, and then curve them through robotic means. And then we have developed customized slip washers, which would allow us to place the washer in a more efficient assembly manner. And the threaded rod, which is the hardware that actually connects all the A-frames together. And that we also utilize augmented reality to help us position the nuts location on the threaded rod. So these are all ways to facilitate the fabrication process. And so here is a drawing that illustrates some of the structure analysis that we have used with Karamba 3D. And in the simulation, we found that the bending active A-frame to have significant structural viability with just a few millimeters of displacement. And here's a photo showing the robot cutting the log, and you can start to see the cut pattern that is alternating from the 2 sides. And next we'll show a video that is a short clip that just shows the log cutting in process. And so here you can see it's also a human-machine interaction where after each cut, we would put a wood block to allow the blade to retract itself. And then it goes on and cut the other side. So back to the presentation. And in this image here, it shows the AR process. So using twin bill, in this case, the AR interface is used to instruct the assembly team on the location of the timber members and also, therefore, their host threaded rods. So through this prototype, so we first developed a full-scale prototype. We were able to understand some of the larger misalignments between the digital and the physical model. And so this physical mock-up was then modified to accommodate some of these unforeseen bending. And then the digital model was updated accordingly. So we used a full-scale mock-up to learn from some of the behavior. For this project, we also developed some fairly simple assembly detail that help us to put together the structure on site. So here it shows the slip wash with the threaded rod and how they connect together with the curved logs. And here's a top view to show, again, the sort of thinness of the bended threaded rod with threading the curved log together. What we discovered also that is really interesting in this project is the sort of material tectonics that begins to emerge from the sort of really precise, clean cut side of the log to the other side where the natural bark remains. And then the image, the photo on the left is the really thin, these are 2 millimeter thick sheathing that we robotically slice from the remaining ash logs that we have left. And then they serve as the sheathing of the structure. So here's a video that kind of shows pan across the installation on site. So the installation has found a new home at the nearby art gallery and community garden, highlighting its mobility. So from unlog to log and back, the structure can be easily disassembled and reinstalled, thus presenting a simple, transportable, deployable, circular, and minimal waste construction method. So after the unlog installation, we went on to decide to explore how can we develop a follow-up investigation and to use the unlog method differently. And so in this new project, currently called the Unlog Tower, we translate the horizontally connected structure into a vertically stacked tower. It is an interdisciplinary collaboration between our other Cornell colleagues, Kirk Jordan from anthropology and Matthew Reiter from structural engineering. Using this technique, the unfolded panels can now be assembled vertically into a tower and sits in the center of the Art Squad on the Cornell campus. And so with the tower, it comes also new design challenge and structural challenges. Whereas the unlog was a horizontal A-frame structure, it performed pretty well itself. Here, a lot more investigation went into how we can develop a structural system, vertical connections, and so on and so forth. And so the project is part of the 2022 Cornell Biennial, and addressing the theme of the biennial, which is futurity is uncertain. The Unlog Tower seeks to broaden the conversation about our shared construction history from balloon framing to the Haudenosaunee longhouses that use locally available materials to build highly efficient structures. So this installation in a way is neither traditional wood frame system nor a traditional longhouse system, but does utilize components exist in various construction methods. And so here it shows the plan diagram on the left, where it's an occupiable space at the base with 3 entrances. And then the drawing on the right shows the how it's made up of various tiers. So the tower is constructed of 4 tiers, and it will be 36 feet in height with an accessible base area of 30 square feet. So the tower, although it explores similar material tectonics in a new structural form, thereby the multi-level structure brought on new challenges, as I've mentioned. Structural simulation using computational tools are developed to test the wind load, displacement, and as well as how to geometrically optimize the transformation of the panel from top to bottom. So you can see in this diagram here that the woods are much denser and closer together in order to accommodate the 3 openings. And it then starts to expand in width, then to full width as it moves to the 4th tier. Again, new connection details were developed, and in this project, we developed finger joints between the panels to resist lateral movement. And here are some photos of one of the panel of tier 4 being stretched out, and some of the hardwares similarly, again, slip washer, except this time is much bigger washer to connect the various tiers. So apart from the robotic kerfing, one of the research investigation we developed for this tower is a bit more on looking at how augmented reality and mixed reality can help us better facilitate the fabrication and assembly of a tower like this, where it involves, again, non-uniform parts, but also non-uniform spacings. And is primarily divided into 3 steps. The first is cataloging, meaning the positioning of the physical log that we're using. Second is the positioning of the log the curve patterns. And third is identifying objects using gestural feedback. And I will show some video clips that explain some of these processes. So the first step in the workflow is actually the simple basic step of mounting the log, positioning it for robotic cutting. But a log is not fully symmetrical and it's non-uniform in nature. So this makes this simple task rather complex because the positioning of the physical log would have to be the same as the digital twin that we're slicing. And so in this video, you see that we can actually, with a fairly straight log, we just need to identify 3 points that would then generate the location of where the log is and how it's oriented on the mount for curving. And then second, we cut the log in half. And again, using gestural recognition here, we're able to then see the curving patterns to check if anything is out of bound of the log. And apart from the log panels, the project uses 6 steel tube frame in a way, the different sections to lock the 3 facades in place. And so each frame actually is slightly different in dimensions. And so for that, that means we have a selection of steel tubes that are also in different dimension. And so again, with gestural recognition, we could touch the 2 ends of the steel tube and it will show us and identify the corresponding component within the frame itself, as well as which tier it is. So essentially, we're using this to help us index our components and parts. And then back to the stretching of the log a little bit more. In terms of the geometric variation, the stretching pattern of the log also determines the cut length. So you can see in this diagram here, the more one spreads, the more varied the length of each of the segments will be. And so what that means is when you have a uniform stretching, symmetrical stretching, like the panel on the left, all their length is fairly the same. But if you see the panel on the right where the stretching is asymmetrical, you will see that the curving distance actually varies from one curve to the next. And therefore, there's implication on our finger joints. So using also similar gesture recognition, we are able to identify the edge of it, and it will tell us where we need to mark, place, and mark and cut the finger joints for each layer. And so some of the examples of the log that we cut. Here, again, similar to Unlock, we use AR to help us determine where the location of the nuts are. And that all facilitates the process quite well. And then when it comes to the installation of the foundation, we're using existing foundation pad where there's previous steel rods from the last installation. And the AR help us to check if there's collision and overlaps between the steel rods that we need to drill for our tower versus the prior installation. So that was a very helpful tool to allow us to double check all that information. And so here it shows the tower now with the panel being assembled together on site. So what we do is we're connecting the 4 tiers of each side first, and then they are then put together on site here, as you can see. So we're assembling the tower horizontally, and here's an interior view of it. This would be the view of what you see when you look up the tower after it's lifted. And this is fresh out of the oven. Actually, we just lifted the tower this morning, and here it shows the crane rotating the horizontal tower vertically and about to lift it and move it in place to the foundation beams on the left of the image. So I will use this image to summarize the last 2 projects. From unlog and back to the log, it illustrates the potentials of new tectonic strategies and sustainable construction methods. I would say in both a very rigorous but also playful manner, our work seeks to leverage technological advancements to reduce material waste and encourages a nose-to-tail usage of logs and timber. And so I'll move to the next project, which is the Ashen cabin that some of you might be familiar with. And so the Ashen cabin was a project that was developed in 2017 and completed in 2019. And in a way, it's accumulation of also some of our research agendas where it combines both 3D printing and also the wood explorations of using waste wood devastated by the Emerald-Ash-Borer. So informed by these two material narratives, it is a small building made of a 3D printed concrete base, structure, and a robotically fabricated timber envelope. In the first material system, the Ashen cabin explored how the horizontal layering of concrete and the act of corbelling can suggest new strategies for building. The concrete structure is printed in components, as you can see in this top view here. And they serve as a sacrificial zero waste formwork for the main structure. So formwork is printed in small sectional modules to be transported and then assembled manually at the remote construction site. And so while the concrete parts can be mass customized with relative ease, as you can see on the left, the subsequent fabrication of the rebar cages does increase in complexity, which required a substantial amount to fabricate. So just to demonstrate that there's upside, but also certain aspect that needs to still be done manually. And so here it shows the concrete components on site. And so for the project, we developed a hybrid construction system with 3D printed formwork and cast in place concrete with custom rebar. Each leg is then filled with foam, and within the void between the legs and the foam, concrete is poured in between to form the main structure. So here you see the structure going up. We're assembling the chimney there. And the slabs are organized in a 9-square grid, reflecting the interlocking pattern of the legs beneath. In this hybrid building process, tectonic expression is generated by fabrication method and its, materiality. So for example, what you see here is the floor tile and the G-code, which is the print path, becomes visible as the ornamental pattern of the 3D printed floor slabs. And corbelling is achieved through sectional transformation and becomes an expressive and functional motif, which then allows the horizontal layers to seamlessly transition from the leg to the slab and then to the chimney above. The resulting concrete structure lifts off the ground and is characterized by 3 programmatic areas. So that was when we just finished printing, as a table, as a storage seat element, and a 7-meter tall fireplace. Due to their geometries, many infested ash trees cannot be processed by regular sawmills and are regarded as unsuitable for construction. So, challenging preconceived notions about material standards in wood, the cabin utilizes infested trees for its envelope, which unfortunately are widely considered as waste or used as firewood. And so for that project, we developed a process that involved 3D scanning and our custom robotic platform, where we can then transform these irregularly shaped waste wood into an abundantly available, affordable, and morbidly sustainable material for the Anthropocene. So with this method, we can slice these irregular tree logs into naturally curved boards and strategically assemble the boards to form different surface conditions. Ironically, to achieve advance environmental resiliency through architecture, our resources themselves are sometimes not resilient enough. And so by adjusting the thickness of each cut, the robotically carved boards can be assembled into single curvature or double curvature surfaces. And so here's an example between the form finding process of the log and the final assembly. And so there is a sort of feedback back and forth between the building design and the logs that they come from. So you can see here in this image where the logs are sliced with different varying thicknesses. And then the slice boards are arrayed into an interlocking SIP facade panels. So SIP is structurally insulated panel. And you can see here the interior elements are more straight and the exterior elements are more curved depending on the logs, and then there's spray foam in between. So for us, certain disciplinary problems, questions of joinery, material connections, proportion, and performance begin to infuse our discussion. Here, the facade assembly, you can see, is a corner moment of how we decided to turn a corner to negotiate the different curvature of the log. The facade assembly is fully ventilated, detailed to manage shrinkage, and does not require an additional ring screen. So the end result of these constant negotiation is an unfamiliar hybrid between digital and the anachronistic processes of construction. And so we think that architecturally, the Ashen cabin walks the fine line between familiar and unfamiliar, between technologically advanced and also formally elemental. And as mentioned, on the inside, we use our predominantly straight ash tree sections to create a contrast between the exterior and interior. So for us, when we were working on this cabin, the project in a way was no longer bound to the paradigm of timber standardization. And the project revisits woodcraft and design based on organic, found, and living materials. While transformed after sliced, the natural tree remains legible in the design. So at certain views, the log actually began to reconstitute itself. But what is more interesting for us is that the cabin combines a variety of fabrication methods, material applications, geometries, and types of constructions. And so again, being rigorous and also being playful, the research in this robotic timber fabrication and concrete 3D printing embraces a complex set of layered design narratives, leveraging technological advancements to reduce material waste, and again, to think about how new expression can come with some of, by thinking about the digital processes from bottom up. So from the Ashen cabin, as a first step to translate some of the methods into small building, we are currently working on scaling up to think about 3D printing, how we can scale up and build larger building system, particularly think about housing. How do we develop housing systems using 3D printing? And so this last project that I'm sharing is actually work in progress. We just started the construction this summer. It is a project. The project is accumulation of 2 years so far. It has been 2-year collaborative effort between boundary pushing design researchers and industry partners. So this project is spearheaded by Hana along with Perry 3D Printed Construction, which is an international leading provider for 3D printing, and CIVU, one of the leading engineering and design build contractors in Houston. So the project started with the intention to think about how we can develop a design using 3D printing to construct modular housing. Even though the project is a single family house, the design logic in a way is meant to be scalable and applicable. So I'll show a video of the project that we have that kind of describe the beginning process from foundation and to where we are. So what's unique about this project is that it is the first 2-story 3D printed building in the country, in the US. And the goal for, again, as I mentioned, for our team is to think about how we can develop the sort of modular aspect. And so you can see it's actually a fairly linear site. And we use, here's Perry using their Cobot 2 modular printer, which then allow us to actually not only go in length, but also in height to 3D print a multi-story condition. And so the design used a hybrid construction systems, meaning that it actually pairs 3D printing with wood framing, making it one of the first 3D printed building to integrate, to use wood framing in an integrative manner. And it is a 4,000 square foot project that showcased the possibility of 3D printing technology, its benefits of mass customization and design solutions, that comes with this method. So we'll return back to the images. And so the project also developed detailed solutions with some of our key building industry partners, from the construction material to HVAC system. So for example, in this project, we are using Quickrete's new generation of their specially formulated 3D printable concrete. And the mixtures, similar to conventional concrete as well, we can integrate fly ash and other waste material to reduce the carbon footprint of the material mixture. We also work with Huntsman Building Solution and their R&D team to integrate their closed cell spray foam product for the printed walls. And so here's an image where you see we're printing on top, and then the bottom section has been spray foamed. And along with that, there's also questions about connections, details. And so we're partnering with Simpson Strong Ties, using some of their connection products to connect the 3D printed elements with our wood connections. In terms of HVAC system, we're actually using Toshiba Carrier's VRF, which is called variable refrigerant flow technology, that is more common for commercial application. And we're using this in a residential context because it allows each section of the building or the rooms or space to have their own control, so that when it does get scaled up to multifamily housing, the integration of HVAC system is also ready for multiple units. And so given that it's a 2-story building, with the structural engineering expertise from our local GC, CIVE, our team were able to develop an approach to printing the second floor. And so you can see in this image that this section here is actually where we cast rain beams, which allow us to continue to print on the second floor. And also the project highlights some of the exciting design potential for mass customization. And so for us to start designing, it was very important to understand the particular material mixture, how it behaves on site with this particular printing system that Cobot has. So we started on site by doing a series of test print from testing different radius and how to turn, the tightness of turning corner to find the optimal dimension and so on and so forth. So actually this is from one of the first test print that we did to identify what turning radius is most suitable for our particular context. And here you see the first section, the printing starting to begin to go up, and the corbelling, the sort of incremental cantilever, again, is used as a design motif in here, where at a larger scale, it translates into these various level of ledges, not only as an architectural motif, kind of an ornamental aspect, but it also helps to break down the volume of the printed mass. So here is a view looking into what would be the living room, which will be a wall of customized shelvings that we're developing here, and the same pattern would move up into the second story. And some photos to show the detail of some of the printing, how the ledges and the offsetting is repeated not only on the interior of the building, but also on the exterior of the building. And so a lot of these design efforts aim to increase the impact, the applicability, sustainability, and cost efficiency of 3D printing for future residential and multifamily buildings in the US. So with this last slide, returning to the cabin, as seen in several of our projects, by fully unpacking the manufacturing process from the ground up, it thereby presents an exciting opportunity for designers to reclaim authorship over new processes of constructions. And so lastly, I would also like to emphasize that all our projects are team efforts, and we wholeheartedly thank our amazing and dedicated collaborators and team members in all the work that we have built and constructed so far. And thank you for your attention. And this is the end of the presentation.
Thank you so much, Leslie, for sharing all of those incredible images and for giving us some insight into the design of the construction methods and the construction methods behind these different structures. I think it started a really already very interesting conversation in our questions tab. And I'm hoping that it's gotten people thinking. For me, thinking about using waste wood is really an exciting possibility. I think there's been a lot of a growing discussion around using timber in architecture, but the fact that we have waste wood materials from ash borer, for example, which has been a big issue up in the area of Canada that I'm from as well, and it's largely used as firewood, is really, really exciting. And yeah, I can't wait to see more uses of it. Without any further ado, I will dive into the questions. We only have 12 minutes left. So one person, we have a lot of kind of practical questions about some of the stuff that you're doing. So I'm gonna just start with those and some of the more popular ones. Chelsea was asking, what are the programs that you're using for design and AR interaction? And how do these programs work together to facilitate your design? What limitations did you find? And how do you foresee AR being used in construction and design in the future?
Yeah, so for our AR, augmented reality and mixed reality application, we use Hologram and Twin Build. And so and along with HoloLens, the Microsoft HoloLens. And what these tools allow us to do is we're also thinking about other layers in terms of instructability and user friendliness. How can, let's say, a user that had no necessary prior knowledge of, the more in-depth, let's say, scripting and computation skills, how can we engage them in the construction process as well? So with the AR and MMR, what it does really well is it provides simple holographic instructions. And so what we do custom on our side is to develop the script, which then that is unique to each of the operation that involves in different steps of the project. And so basically it's a workflow with Rhino Grasshopper and then Hologram or Twin Build, then into the Microsoft HoloLens set. You can also use iPad, for really quick, let's say, checks, then we can use the iPad. Now, one of the challenges using the current AR and MR tools, the state of the art, is that they do tend to drift sometimes. What that means is you might have an origin 0, 0, 0, but then after you move and walk around a bit, the model actually starts to move. So they're not 100% accurate anymore. And so depending on the type of task that you're doing, sometimes very high tolerance is really important, and sometimes it's okay if things are a little bit with a bigger tolerance. And so really very much depending on the task that we're doing, and so then we would use the HoloLens for more precise work when it comes to constructability. And so regarding the future, we definitely see a role in this, especially, with our Unlock Pavilion and actually the Tower project. The MR and AR is already making a huge difference in our process, that we're actually using the scripts and these tools that we develop to help us position, to help us check the positioning of the design, and also actually providing instruction when we have a new team member coming in. It's pretty straightforward. It's like, here, read the instruction, what you see, and this is what you need to do.
Thank you so much. So a follow-up question to that would be, have you ever used other types of, have you ever used other types of wood or only ash? Someone else was also asking about using bamboo, I saw in the chat. So that's kind of an extension of that. And if so, does the stretching and dimension requirements need to change for the different types of wood?
Yeah, so we've been using mostly of the free ash logs that we have in our backyard, not our backyard literally, but at in Ithaca and at Cornell. And so quick question regarding the bamboo. Yes, because actually in my Ruby lab, we actually are exploring bamboo as well, particularly with AR and MR tools, because bamboo is even a bit more non-uniform, given that there's nodes and the spacing of the nodes are different. And so we do have ongoing research with bamboo as well. Now, regarding ash trees, we found actually ash trees to be a really fantastic wood to work with. And I think that also there's a question there that asks, do you cure the wood before installing? If not, how do you expect the drying curing of the material to change the final design? How do you see this material weathering over time? So I'll speak more specifically to ash tree first. We use white ash, which is a fantastic timber because it has a fairly low humidity to begin with, and so we actually don't have to cure them as much. So they usually, for our structure, we didn't really go through like a curing process because I think it was already begin with like a 14% humidity or so on and so forth. And so we haven't experienced that much when you slice them in terms of checking or cracking. That hasn't been really a problem. And then another thing that's really nice about ash wood is also over time, for example, with the cabin, we left it untreated, so it would gray over time. And so now when we visit the cabin, it's not this warm wood tone, but rather it's kind of this sort of gray wood texture that speaks to also complement the concrete, the grayness of the concrete as well. So we do allow the material to weather over time and then to transform from the warm to the gray coloring. And if we were to use a different wood, I would say in the Unlog Pavilion, it's less so of a concern, but more so in the tower, because the tower, the structure requirement is a lot more stringent and rigorous. And so when we do the structure analysis, we do input the elasticity, basically all the property of the white ash in our structural simulation. So if it's a different type of wood, it would also then have different structural material property that we would integrate, that then would probably consequentially affect how thick you need to cut versus how much you can stretch.
Someone was actually asking specifically how thick you are cutting. Like, we have a few very practical questions. So I just wanted to slip that in while you said thickness.
Yeah, for the Unlock Pavilion, the curve is half an inch thickness. And for the tower, the thickness of the curved section is scaled up to 3/4 inch.
And that's based on the needs of the structure.
Yes.
Okay.
Yeah.
Thank you.
Structure calculation. So we work with our colleague from engineering, who then work with us together to find the required thickness in order to withstand, for example, in Ithaca here we have the building code wind load requirement of 105 miles per hour, and so so that's the sort of requirements that we have to kind of meet. Yeah. I know.
I was just wondering before we were talking about erecting the tower this morning, and I was just wondering if it was windy this morning when you were putting it up.
Oh, it wasn't raining. It was raining, so we were in the rain. Yeah.
So I'm going to ask one more question, but before I do, I just want to let everyone know that there's a poll, which is in the polls tab directly next to the questions. You'll find it in the lower right-hand corner of the screen. And so if you're interested in potentially participating in an event like this as an A+ award submitter, we'd love to hear from you. And you can just let us know by responding to our poll, and we'll send you some more information or a submission guide to the upcoming A+ awards program, which is launching this October. And so with that, I'm going to ask one more question. This one was it's the most popular right now on the board, and it's both pragmatic and practical, as Adam says. He says typical concrete placement costs about $400 a cubic yard for the material and the labor once placed. Specialty 3D mixes run about $600 a yard. How do you see bringing the price down so that it become normalized in the construction industry in general?
Yeah, actually, in the past few years, we've already seen huge leaps in terms of 3D printing concrete mixture. Whereas, before there might be more proprietary mixture using, with specific printers. Now, there are many more large cement manufacturers who are now developing their own concrete mixture. So one aspect is in the coming years, you will see there will be more and more available 3D printing mixtures, and that will bring the cost down. So that's definitely, we already see it happening. And then the other aspect is less of a straightforward answer, because it's not about just how much a cubic yard costs, but rather the type of labor and time that you save. So for traditional concrete structure, the material might be cheaper to start with, but you have to build the formwork. So you need the labor to build the formwork. It takes time, and then you have to, you pour the concrete, then you have to remove the formwork. Essentially, with concrete building, you're kind of like building a building twice. Whereas with 3D printing, you skip that process, where you skip that step, and a lot of the printers could be run with much less people, a smaller staff and a smaller crew. And so we're hoping also through this project then to get a more kind of an overarching view of actually the cost of it, because it's not just about the material, but it's also about the type of labors, the number of hours that 3D printing concrete might save, so as to offset the material cost. And so we do see it being normalized, and I do believe that 3D printing concrete will become one aspect, like a normal aspect of building construction techniques. It's not going to take over everything, for sure, because our construction industry is very diverse. And so it's not about, oh, this is the one thing that will solve our problem, but rather it can be leveraged in very strategic ways in terms of how we can build differently.
Thank you so much, Leslie, for taking the time to prepare this in-depth presentation. The entire PowerPoint itself, in addition to everything that you said, was really stimulating and exciting. And I think that these types of conversations about where architects can also innovate in the construction process itself, fabrication methods, are really exciting and underexplored. So thank you for starting this conversation. We still have so many more questions that are unanswered. Maybe I can send some of them to you as well, but I think that that's for me editorially a gold mine of thinking about the types of conversations we'd like to continue having. So thank you so much. I'll be back again tomorrow at 11 a.m. Eastern in conversation with Yasemin Kaliglu, who's a principal at Skidmore, Owings and Merrill. She's also the Sustainable Design and Climate Action Leader there. And we're going to be discussing SOM's new prototype for a carbon removal system in buildings, which is viable today. So I'm hoping to see you all there. This talk, if you've come in late, is going to be available as a recording immediately after the presentation. Thank you again, Leslie, so much. And thank you to everyone who attended. And I'm looking forward to seeing everyone again sometime.
Great, thank you. Bye.
Thanks, bye.